Today we're going to be going over Physical Science Module 15, and the topic is light. Light is a type of wave that causes objects to be visible to the human eye. The sun produces light, and that light bounces off objects into our eyes. Our brains interpret that light and tell us what we're seeing. But what is light, and how does it work? Scientists have been working on the answer to that for hundreds of years. Dr. Weil first talked about the particle theory of light. The particle theory of light was proposed by Sir Isaac Newton, and he explained it in his book entitled Optics in 1704. There were several things that he had observed about light and that led to his theory that light is a particle. First, he noticed that light reflects. When light reaches a smooth surface, it bounces off that surface, just like steel balls bouncing off a smooth surface. And so that led him to believe that light was acting like a particle. He also noticed that light, when it reaches a barrier, it stops and there's a shadow beyond it. He pointed out that we can hear sound from behind an obstacle, but we cannot see light from behind an obstacle. So that said to him that light was a particle and that obstacles could stop it. He also noticed that light always travels in a straight line, that it doesn't bend around corners like a wave would do. And finally, he noticed that light is able to travel through a vacuum. Waves are not able to travel through vacuums. Remember, when we were reading about waves and sound, waves need a medium to travel through. So he decided that light must be made up of small particles of energy, and he called those particles of energy corpuscles. And here we have a little diagram of how he imagined light as corpuscles. Next, Dr. Weil talked about the wave theory of light. And the wave theory of light was proposed by a Dutchman named Christian Huygens. He explained his theory of light in his book entitled The Treatise on Light in 1690. So he was a little bit earlier than Sir Isaac Newton. They worked independently, though. He based his theory on several observations. The first observation was that although he also noticed that light reflects, he argued that waves will also reflect. That's how we hear echoes, because sound, which is a wave, will reflect back to us. But he also noticed that light would refract, that when it goes into a different medium, let's say it's traveling from air into water, that it doesn't continue to go in a straight line, it actually bends. And so he theorized that was proof that light is a wave. He also noticed that when light passes through a narrow slit, it becomes wider. The beams actually spread out and become wider than he expected them to become. And so he theorized that light is made up of waves, and he said that these waves produce wavelets, and actually what's coming at us when we look at light is a wave front. Some had argued that if light consisted of particles, then when two beams of light crossed, some of the particles would collide with one another to produce a deviation in the light beams. Huygens was able to demonstrate why light rays don't crash into each other when they cross paths with his wave front theory. An English physicist named Thomas Young later performed an experiment showing that when two beams of light cross, they actually do interact. They become brighter. This revelation became known as constructive interference. But Young's observations were still consistent with the wave theory. One thing that was an argument against the wave theory was the fact that light passes through a vacuum. And so Huygens was aware of the fact, and so he theorized that there was a medium in the vacuum that we needed to discover, and he called that medium ether. And for over 100 years, scientists were looking for this ether that Huygens said must be there for light to travel through. that it was the medium in a vacuum that light traveled through. And of course, we know now that ether does not exist, that there really is nothing inside a vacuum. And so scientists sort of wasted their time for hundreds of years looking for the ether. The reason why both of these theories were valid was because light does behave sometimes like a particle, and sometimes it behaves like a wave. And if you recall, Dr. Weil mentioned that it was the quantum mechanical theory of light that brought the two theories together, that harmonized them. Now, the quantum mechanical theory of light was first proposed by James Clerk Maxwell. He introduced it in his treatise on electricity and magnetism in 1873. He had observed that the speed of an electromagnetic wave is approximately the speed of light. In fact, in 1862, while he was lecturing at King's College, Maxwell calculated that the speed of propagation of an electromagnetic field is approximately that of the speed of light, and he considered this to be more than just a coincidence. Commenting on it, he said, "We can scarcely avoid the conclusion that light consists in the transverse undulations," remember undulations are just vibrations, "of the same medium which is the cause of electric and magnetic phenomena." So Maxwell's experiments and conclusions led to the generally accepted quantum mechanical theory of light. He didn't actually name it. He didn't actually say, "This is my theory, everybody should believe it." He just shared his findings with the world in his treatise on electricity and magnetism, and other scientists sort of ran with it and harmonized the wave theory and the particle theory. In the quantum mechanical theory, as you read, light is both a wave and a particle. We call these little packets of energy a photon. Now, before we go any further, I'd like just to review transverse waves very quickly. Remember that a transverse wave is a wave where the disturbance that makes up the wave is moving perpendicular to the direction in which the wave is traveling. And so you can see on the diagram that the wave is oscillating or vibrating up and down while at the same time it's traveling out from the woman in the diagram. So the wave is vibrating or moving perpendicular to the direction in which the wave is traveling. Remember that the highest point on a wave is the crest and the lowest point is the trough. And when we measure from crest to crest or from trough to trough, we get the wavelength, signified by the Greek letter lambda. If we cut the wave in half, we can measure the height of a crest or the depth of a wave, and we can get the amplitude, which is signified when we do math problems as the capital letter A for amplitude. Remember that we can also discuss and calculate the frequency of a wave, as well as the speed of a wave. Remember that the frequency is how many times the wave hits a certain point every second. And that becomes important with light. It's not just important in sound, but it's also an important concept in light. Now, an electromagnetic wave is a special kind of transverse wave. In fact, this diagram is somewhat complicated, but hopefully we'll make it a little less complicated. Notice that an electric field is vibrating vertically while a magnetic field is vibrating horizontally on the electromagnetic wave. The definition of an electromagnetic wave is a transverse wave composed of an oscillating electric field and a magnetic field that oscillates perpendicular to the electric field. Remember that oscillating means that it's vibrating. That's all it means. And if something oscillates, it means that it vibrates. Also, it's important to note that it is a wave, and because it is a wave, it will have a wavelength, and we can calculate the frequency of wavelengths using our frequency equation. Luckily, though, this chapter doesn't require you to do that. There are many kinds of electromagnetic waves, but in order for light to be produced, both an electric field and a magnetic field must be present, and they must be vibrating perpendicular to each other as well as perpendicular to the direction in which the light is traveling. So again, the quantum mechanical theory of light tells us that light consists of tiny particles which have wave-like properties associated with them. We call these light particles photons. And so instead of one continuous wave, what we would really have is packets of waves. And so they would look more like this than the continuous wave on the diagram that we've been using so far. Now, scientists have been able to calculate the speed of light, and in the book it said that the speed of light is 300 million meters per second, which is about 670 million miles per hour. That's pretty fast. I think I've read that light reaches Earth from the sun in about 8 minutes. Light moves faster than sound. The speed of sound is only 340 meters per second, which is about 760 miles per hour. 760 miles per hour is pretty fast, but not nearly as fast as 670 million miles per hour. So light is moving a lot faster than sound. Light is not dependent on temperature like sound is. Light travels fastest through gases. Remember that sound actually travels faster through solids than it does through liquids, and travels faster through liquids than it does through gases. Light is the opposite. It travels fastest through gases, slower when it gets to liquids, and even slower still, or stops altogether when it reaches a solid. The speed of light in a vacuum represents the maximum speed that can be traveled by any object that has mass. On Your Own Question 15.1 asked, which of the pictures below is the best illustration of the quantum mechanical theory of light? And you'll notice that we have 3 different diagrams there. In A, we notice that there's an electric field and a magnetic field in that wave. B shows you little packets of waves, and then C shows you little particles. And so the quantum mechanical theory says that light is little particles that behave like waves, and so B is going to be the answer. It has a series of photons. On Your Own Question 15.2 asked, suppose a photon is traveling through air. If the particle suddenly hits a lake, what will happen to its speed? And so remember that as light passes from a gas to a liquid, that it slows down. So the answer is light is going to slow down. Just as wavelength and frequency of sound determines how our ears interpret sound, remember that high frequency sounds have a high pitch and low frequency sounds have a low pitch. The wavelength and the frequency of light determine how we see the light. Different wavelengths of light appear to us to be different colors. Wavelengths of light are measured in nanometers, and a nanometer is like 1/billionth of a meter. We don't have to know that for class or anything. I just thought that that was interesting. We're often told to memorize the order of the colors in the visible spectrum, or the rainbow, by memorizing the mnemonic device Roy G. Biv. So R stands for red, O stands for orange, Y stands for yellow, G stands for green, B stands for blue, I stands for indigo, and V stands for violet. Remember that short wavelengths give us high frequency because there are more of them passing by a certain point in any given second. And long wavelengths give us low frequency because there are fewer of them passing by any given point in a second. So, experiment 15.1 was an experiment that discussed how rainbows are formed. And you can see on the diagram here that light from the sun comes into a drop of water, and when it does, it slows down when it's passing from the gas, the air, into the water, the raindrop. It actually slows down and then it bends, and we call that bending refraction. We're going to talk more about that next week. Then it hits the edge of the water droplet and it actually gets reflected back into the water droplet. We're going to talk about reflection in just a few minutes. Then as it passes from the water droplet back out into the air, it bends again or is refracted again, and then what we see is we see the rainbow. And so experiment 15.1, we saw that light went into the water, and as it went into the water it bent, and we call that bending, as I said, refraction. The light was reflected back out of the water by the mirror. Then as the light left the water, it bent again, and the result was a visible rainbow on the wall of our room. I went ahead and did a video of us doing experiment 15.1. Hopefully you did it at home, but if you didn't, on YouTube I am going to post a video of us doing that, and so that you can see how experiment 15.1 was supposed to work. And so from this we can tell that white light is really light that's made up of many colors, and if we separate the wavelengths we see the different colors, and that's something that you read about this past week. Notice that the different colors of light in this diagram have different wavelengths. They aren't wildly different, but they're enough of a difference that they have different qualities to them. Violet has the shortest wavelengths, and so it's going to have the highest frequency, and red has the longest wavelengths, and so it's going to have the longest frequency. Just as there are sounds above and below our ability to hear, there are also electromagnetic waves that have wavelengths and frequencies that we can't see. We call the electromagnetic waves we can see the visible spectrum. In order to talk about the electromagnetic spectrum, we're going to have to turn the visible spectrum around, at least for this particular book. I've seen some books that go ahead and keep the spectrum the way that we memorized it, Roy G. Biv, but for our book, we're going to have to turn the visible spectrum around. And so do you see what I did there? I'm going to go back real quick. And you can see that we've just turned the visible spectrum around. We can still remember Roy G. Biv, but we're going to have to remember it backward. And when we put the visible spectrum into the electromagnetic spectrum, you can see on this diagram that it is just a small fraction of all the electromagnetic waves that are actually coming from the sun. Over to the left of the diagram, we start with gamma rays. And I've gone ahead and colored them green. They're red in your book, I think, because the Incredible Hulk, if you recall, became the Incredible Hulk because of his exposure to gamma rays. And you'll notice that on the spectrum that gamma rays have the smallest wavelengths, have the highest frequency. And so if you recall from the chapter that we did on alpha and beta and gamma decay, that gamma rays are the most destructive to human bodies and to everything else, that they are very powerful, highly charged rays and very destructive. Next on the electromagnetic spectrum are X-rays, followed by ultraviolet light, and we've got a lovely young lady there who's putting on her suntan lotion so that she won't be hurt by the ultraviolet rays. Remember that ultra means beyond, so ultraviolet are the rays that are beyond violet. And they are definitely rays that we can feel. We can feel the heat from the sun, and we can feel ourselves burning as we're exposed to ultraviolet rays, but we can't see them. On the other side of the visible spectrum, we have infrared light. Remember from sound that infra means below. So we have ultraviolet, beyond violet, and then we have infrared, which is light that is below red. And the reason we say below is because in terms of the wavelengths and the frequency, the wavelength and the frequency are below red on the electromagnetic spectrum. And I have put a little remote control as the picture to remember infrared light. I think he had like an infrared poker or something like that. But most remote controls use infrared light in order to change the channels on your television sets. Beyond infrared, we have microwaves. And Dr. Weil discussed microwaves and how microwave ovens simply shoot microwaves through your food. They're absorbed, the microwaves are absorbed by the water in your food, and the atoms of water start to vibrate. And as they vibrate, they cause friction. And remember when we were talking about the frictional force, we discussed how friction will build heat. Unfortunately, it's not a very long-lived heat. And so things that warm up in the microwave warm up quickly, but they don't stay warm for very long. Beyond microwaves are television waves. And then finally, we have radio waves. Now remember that television waves and radio waves, I have a lot of students misunderstand. And actually our textbook is a little outdated because television waves aren't even used to beam television programs into our homes anymore. But in the old days they were, and they were picked up by antennas. And so television waves are not waves that you can see. They are simply electromagnetic waves that a transponder would take the audio and visual from a television program, and it would translate it into an electronic signal, and then it would ride these television waves until it got to your home and your antennas, and then it would come down into your television, and then the television would translate those electronic waves back into audio and visual so that you could watch your television program. So television waves themselves are not things that you can see and things that you can hear. They are simply electromagnetic waves that television signals were able to ride to get to your house. And the same with radio waves. Radio waves are all around us. They are not waves that you can hear. They are not sound waves. They are simply electromagnetic waves that the transponder at a radio station can translate the music into electric signals rather. And then they can ride these radio waves until they reach an antenna in your car or in your home that can pick them up and then translate them within the radio back into sound waves that we associate with listening to the radio. So once again, I don't want you to misunderstand what television and radio waves are. They are just vehicles for these forms of entertainment that we have invented. Notice that at the left side of the electromagnetic spectrum, down by gamma waves, that we have very short wavelengths, and at the other end, at the right side of the spectrum, where the radio waves are, we have much longer waves. And the same with the visible spectrum. At the left side, where there is violet and blue and indigo, we have short wavelengths. And at the side where we have red, we have long wavelengths. On your own question, 15.3 asked, without looking at figure 15.2 or figure 15.3, order the following colors in terms of increasing frequency: yellow, indigo, red, green. And so if I were approaching this question, if I were a student, the first thing I would do is I would write out my Roy G. Biv. And so you have permission to do that if a question like this turns up on your quiz or on your test. The first thing you should do is go ahead and write down Roy G. Biv. Remember that at the right side where red and orange are, you're going to have long wavelengths. And at the other side, where you have violet and indigo, you're going to have the short wavelengths, which means that Over by red and orange, you have low frequency. Long wavelengths mean low frequency. And at the side by violet and indigo, you're going to have high frequency. Short wavelengths mean you have high frequency. So the first color you're going to list is red because it has the lowest frequency of all. Next comes yellow, then green, and finally indigo will have the highest frequency out of that list. On your own, question 15.4 said, if radio signals are really made up of electromagnetic waves, why doesn't a radio station's antenna glow when it transmits its signals? And of course, the answer to that is that radio waves are not part of the visible spectrum. They're part of the electromagnetic spectrum, but they're not part of the visible spectrum. The next part of the chapter was a discussion of reflection. That was one of the things that Isaac Newton about light and helped him develop his particle theory of light. And so there's a couple things that I want to talk about when we're talking about reflection. Now, when it comes to the word reflected ray of light and the angle of reflection, I think most of us understand that because you are very familiar with reflection and the vocabulary that comes along with that. Remember that reflection is the throwing back of light, heat, or sound without absorbing it. And so things that are reflected, they come in to the surface and they're shot right back out. Now, on the other side of this diagram, there's the vocabulary incident ray and the angle of incidence. And often students have some difficulty understanding what the incident ray and what the angle of incidence are. And so I wanted to define what incident means. In everyday life, an incident is an event or an occurrence. You might get into trouble and you might have to confess the incident that happened while mom and dad were gone. In science, incident means simply the light falling on or striking something. So remember that the law of reflection says the angle of reflection equals the angle of incidence. So the angle of light reflected out is equal to the angle of the light coming in and falling on or striking something. And you can see in this diagram that is very well illustrated. In this diagram, we see a woman looking into a mirror, and she sees the image of a bottle reflected on the mirror. Remember when Dr. Weil was discussing reflection in a mirror in the book, that he explained that the eye gathers in light and it passes on the electrical impulses to the brain from that light. And then the brain converts those electrical impulses into an image. And so our brains are used to seeing light come straight into our eye. And so when we see images in a mirror, our brain is assuming that the light from those images is still traveling in a straight line rather than being bent because of reflection. And so as a result, our brain extends that light backwards, as illustrated by the dotted lines there. And so it seems as if the image of the bottle is actually behind the mirror rather than on the surface of the mirror. Our brain projects that image back three-dimensionally into the mirror, into the plane of the mirror. And we're going to look at that again in a simpler diagram on the next slide. Now this diagram is more like what you're going to actually see on a quiz. Now notice on the diagram that you have an object, and the object is projecting an incident ray of light. In other words, the light is just coming from that object and it's hitting the mirror and reflecting back up into your eye. Notice that the angle of reflection in this diagram is equal to the angle of incidence. And then notice also that the image that you see, that your brain, because it wants to make logic out of the world, will go ahead and project that image back. Even though the image is right on the surface of the mirror, our brain goes ahead and logically it has to be back away from us. And so it projects the image back onto imaginary space within the mirror. And so the image there looks as if it is far away from us, even though it's just right there on the surface of the mirror. On your own, question 15.5 said, draw the path of the light ray in the diagram below to show where the light eventually hits the screen. And so I don't know if you did it in your book or if you copied it onto a piece of paper, but basically what you're wanting to do is you're wanting to, from the incident light, you're wanting to have a light beam that's reflected, and if you want to draw it so that the angle of reflection is equal to the angle of incidence there. Then it strikes the other mirror, and once again you want to draw another beam of light coming out, and again you want to make the angle of incidence equal to the angle of reflection, and so you can see how the light would end up hitting the screen there. This is a really important diagram. It is going to show up on your quiz, so I just wanted to go over it one more time. Notice that you have an object that is releasing an incident ray of light into a mirror, and that a reflected ray of light is going up and hitting the eye of the beholder. The angle of reflection is equal to the angle of incidence in that diagram, and then the eye sees the image and its brain projects the image back into the mirror so that it makes sense. And that is it for today.